can get comfortable.
Yeah, exactly. Okay, there we go.
Is that about using an overhead?
An overhead? What do you mean?
With the Xerox?
Oh, yeah. That was good times, man. All right, we back. You got no audio on that, but there you go. All right, does that make sense? So again, two levels of understanding, right? One is following the steps and agreeing that each step makes sense from the previous and that the conclusion is undeniable at the end. That's the first level, okay? That's kind of the level that we're at. The second level is being able to synthesize, right? That's the level we're heading towards, which is you're given this and you can come up with this, right? And it's just practice. It's like doing the other kinds of proofs. It's like doing physics problems. It's like solving integrals, right? It's trial and error and it's practice. And you just kind of keep hitting it and it gets better over time. But the more different kinds of problems you tackle like this, the more that intuition is going to come. So let's try a totally different kind of proof. So picture a tiled floor and picture these tiles that are L-shaped. And they occupy exactly 3 of these squares on the floor. And you can rotate these tiles in any direction you want. You can flip them over. And your goal is to try to cover as much of the floor as you can using these L-shaped tiles without having any overlap and hopefully without having any regions uncovered. And so we can start off, we might drop a tile down here and another one over here. And another one down here. And maybe put one in here. And we're going to have a problem here, right? So it's like a Tetris thing, right? And our goal is to try to find a way to tile this floor completely. No overlaps, no broken tiles, no missing places. All right, well, there is a theorem which says if you have a tiled floor and each side has length 2 to the n, so 2, 4, 8, 16, 32, etc. So n bigger than or equal to 1. And you have exactly 1 hole. So somewhere you have a tile that's a spot that's missing on the floor, a spot you don't want to cover with a tile. Okay, you have exactly 1 hole. Given this setup, square region 2 to the n by 2 to the n on each side with exactly 1 hole, you can cover it perfectly using these L-shaped tiles. That's our theorem. Okay, everyone clear what the mission is here? You got 1 spot, maybe that's where your power outlet is, and so you don't want to cover that up, right? So you're going to have 1 square that's not covered by a tile, but you want everything else covered by a tile, and your region is 2 to the n by 2 to the n. The claim is that you can always achieve this tiling as long as n is bigger than or equal to 1. And we can prove this. So we need a proposition. Let P of n be the proposition. You can tile 2 to the n by 2 to the n floor with one hole using L-shaped tiles. Is that a valid proposition? It's a declarative statement. It has a true or false value for any given value of n. For n is 5, it says given a 32 by 32 floor with one hole, we can tile it using L-shaped tiles. That's a declarative statement. Could be true, could be false. Nothing mathematical in there except the 2 to the n part, right? But no summations, no derivatives, right? A very sort of casual sounding proposition, but it's still a proposition. And it's a proposition we can use mathematical induction on. So what's our first task with mathematical induction after we've stated what P of n is? P of 1, base case. So you want to prove P of 1. So P of 1 is talking about 2 by 2 floors with a single hole. Well, there's 4 cases. Because since there's only 4 tiles, there's only 4 places our hole could be. It could be here, 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 or here. And so we need to show that in each of those cases, we can tile the floor with an L-shaped tile. Am I shouting? I'm kind of shouting. Can we tile this floor with an L-shaped tile? Sure, we can go like that. Can we do this one? Yes. Can we do this? Can we do this? We've just proven P of 1. We've proven that for any 2 by 2 floor with one hole, we can tile it because we've shown how to tile it. So P of 1 is true. All right, we're halfway done. Inductive step. I know what that was. Prove that given P of n, we can conclude P of n plus 1 for any n bigger than or equal to 1. Well, this is really subtle. Okay, I never would have figured this out, but somebody did. But here's how we can, does anybody have any ideas, first of all, how we might tackle this?
Well, I don't know how to prove we can fill a tile of any size.
Say again?
I don't know how I can fill a space of any size, how to prove I could without doing it. I have it.
Yeah.
So it'll be like, so right now 3 of the 4 squares are covered.
Mm-hmm.
Each time you increase n by 1, the total area increases by 4 times, right?
Mm-hmm.
So if you were to tile, say, that first pattern in just an array of 4 by 4, you would have a total of 4 empty squares.
But they might not be next to each other.
Not necessarily next to each other,
Mm-hmm.
but the aim then would be to cover 3 of those squares, right?
Right.
So say you rotate each pattern such that those 3 empty squares are lined up next to each other. Basically, you could use some combination of these 4 tiles above to
Interesting
make something
idea.
that, you know.
So
could be
that
matched up.
might work. The question is this rotate function. Can we make that rigorous and show that it will always work? And intuitively, I like it. I think that might be a way. I should have some tiles we should be able to play with.
Yeah, I mean, you don't necessarily need to rotate it because all 4 of these are just, you could say that each of the last 3 are just the first one rotated.
Mm-hmm.
But yeah, basically my thinking is as long as you keep the empty spot on the corner of the latest iteration of the pattern that you're working with.
Okay.
And combine 4 of that in such a way that you make a perfect, L-shaped space to put in.
All right, I think your intuition is spot on. Did you have an idea?
It's the same thing.
Same thing? Okay. Cool. All right, you're way ahead of where I was when I was working on this. So let's look at this. Let's suppose P of n is true. And let's look at our region for P of n plus 1. So let's draw this out. And this is 2 to the n plus 1 on each side. And we want to know if we can tile it. Well, split this into 4 smaller regions. So this whole thing is 2 to the n plus 1. But the smaller region is 2 to the n. Okay, there's going to be a hole somewhere. I don't know where it's going to be. Suppose our hole is right here. Well, we know that we can tile this 2 to the n by 2 to the n region with L-shaped tiles, correct? We know that because we're supposing P of n is true. So we can tile all of this because P of n is true. We don't know anything about tiling these 3 remaining regions because P of n only applies if we have a hole in our 2 to the n by 2 to the n. So let's put a hole right here in the corner. And now this is a 2 to the n by 2 to the n region with a hole. We can tile that, excluding the hole because of P to the n. And let's exclude this corner, and that lets us tile this region. And let's exclude this corner, and that lets us tile this region. And now we've covered the entire region except for this little L-shaped region of holes. And so we take one more tile and we drop it in there, and we're done. Which is what you were suggesting. And the fact that we started by assuming the real hole was in this quadrant has nothing to do with this proof. If it's in this quadrant, we just do the same thing, but we pop a hole in the corner of those 3. So it's 4 cases to work with, but basically in any of those cases, we can tile the 2 to the n plus 1 region. Therefore, P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. So what do we think about this proof? Love it?
Isn't it? It's pretty cool.
It's fairly painless, right? Go ahead.
Doesn't it also kind of rely on the assumption that you can put the empty space wherever you want it?
So the proposition is that the floor has one hole, right? It could be anywhere. It's not required to be in any particular position. So I probably should have put that up here with one hole anywhere. And in the proof, we only need to recognize that wherever that hole is, it's going to be in one of these 4 regions. And then just argue like this for each of those 4 cases.
Yeah, the remaining 3 regions you can tile in whatever pattern you want, as long as you fill them up.
Right. Yeah. So it's fairly painless to prove if you know this trick, right? Breaking these things up and putting the holes in the corner. We don't really have to do a whole lot of work once we have that insight. It's a 1-page proof with a little bit of hand waving. Whereas if you went about this combinatorically, for example, and tried to look at different arrangements of tiles and whether or not a certain arrangement leaves a hole, and then try to do an existence proof to show that there's at least one arrangement, you could make a really, really long, complex proof, right? And a lot of tiling proofs are very long and complex. It's a big area of mathematics. But this is pretty painless. There's something else about this, and this is the most important point of possibly the whole course. There's something else about this proof that we can observe. Suppose somebody comes to you with a floor that's 1,024 by 1,024 and says, hey, I'll give you $1 million if you can cover this floor with these L-shaped tiles, except for that one hole over there. Well, you've seen this proof, you know it's doable, right? $1 million, probably worth figuring out what the solution is, right? Well, it's a lot of work. It's 1 million tiles, right? But suppose you have a friend who has previously in their life tiled a 512 by 512 floor. And they're just really good at doing that. And you say, hey, you want to make 20 bucks? Tile this floor for me, right? So you can do exactly this. If this is the region with the hole, give them this floor, let them tile it, take a pattern back, mimic that, and say you want to make another 20 bucks and give them this floor, right? Do the same thing, and then this one and this one. And once they've solved those 4 512 by 512 problems, you've got the solution to the big problem. And it didn't take you any work. All you had to do was create a 512 by 512 with a missing corner, hand it off to this person and say, solve this for me, and then use that solution as part of this solution. All right, well, your friend lied. They didn't actually ever solve a 512 by 512, but they know it's possible because they've taken this course also. But they have a friend who solved a 256 by 256. And they're like, hey, you want to make a buck? And so they hand them a 256 by 256 region 4 times. They get the solutions, right? And they can conclude their 512 by 512 problem and hand that to you. You see where this is going, right? Eventually, you're going to get down to somebody who says, hey, you want to make a penny? Can you solve this 2 by 2 tiling problem for me? And you don't need to hand that to anybody. You know how to do that because you worked out the base case in this proof, and you actually saw how to tile those 4 cases. So you can actually solve those problems, make a penny each time, and hand it back to the person. So this is not just a proof that tiling is possible, it's an algorithm for tiling. And that's the real key here. The proof actually becomes an algorithm. And you can code this up by using this proof. And coding it up is exactly what we just described, where you hand things to your friends. That's just calling a function. The really cool part is you can be your own friend. Right? You can say, okay, I don't know how to solve this for 1024, but I'm going to solve it for 512. So you put away the 1024 problem and you just work on this 512 problem. And you say, well, I don't know how to do that. I'm going to cut it in half. I'm going to do this. I'm going to solve this 256 problem. So you put away the 512 and you solve the 256, right? Eventually you'll get down to where you have to do one of these 4 cases. You say, okay, now I've solved the 2 by 2 case. I'm going to put those together. Hey, now I've solved the 4 by 4 case. I'm going to put those together. Here's the 8 by 8 case, and you can come back up for air, and eventually when your head pops up above the ground, you've got the whole solution. That's how we can actually code this. And the whole thing hinges on the ability of a function to call itself. Okay, so this is what a recursive function is. And recursion and programming go together really nicely. And they work really well in data structures. Because particularly when we start talking about trees in another week or two in 222, most of the things we do with trees we can think of like this. We're going to be able to take some problem and express it in terms of smaller problems that are similar. And at some level, this is no different from this other version of recursive functions, where we can say n factorial equals n times n minus 1 factorial. Right, this recurrence relation that we had for solving sequences. Well, if someone wants you to compute 10 factorial, if you know someone who can tell you what 9 factorial is, you can just multiply that by 10. And you're done. Well, how do you find 9 factorial? I don't know, but if I can find 8 factorial, I'll multiply that answer by 9, and I'll be done. So let's look at some code. So let's calculate what 10 factorial is. I do need an extra parenthesis. Alright, so let's print out what 10 factorial is. We're going to write a function called fact that takes an integer and tells you what that factorial is. Bang, we're done. What's n factorial? It's n times n minus 1 factorial. But if I run this, So how do we write a function to calculate the nth triangle number? Same base case, if n is 1, the answer is just 1. But the nth triangle number is just n plus the n minus first triangle number. So I change that star to a plus. And there's our 10th triangle number. Again, we're just using a recursive definition, a recurrence relation. All right, let's look at one more. Given an infinite supply of 5-cent and 3-cent stamps, prove you can make exact postage for any amount n bigger than or equal to 10.
Is that $10?
10 cents. Thank you. So you got 3-cent and 5-cent stamps, as many as you need. Someone wants to ship something for 173 cents. Can you make exact postage with the 5 and 3-cent stamps so you don't have too much or too little postage? And it turns out this is true. You can make 10 cents, so let P of n be the proposition you can make n cents postage using 3-cent and 5-cent stamps only. And P of 10 is true. And we only want to prove this for n bigger than or equal to 10, so we're going to try to show that P of n implies P of n plus 1 for any n bigger than or equal to 10. Maybe I needed to start at 15. Let's start at 15. Just to be safe. Well, we assume P of n is true. That's the hypothesis. What we want to do is increase our postage by 1 penny. This was a bad problem, sorry. Let's do 3-cent and 4-cent stamps. Can't do it with 3-cent stamps. Okay, 5-cent and 4-cent stamps. So P of n is true, so P of n is going to be 15, right, 3 5-cent stamps. All right, if we have a combination of 3-cent and 5-cent stamps, there's two possibilities. P of n's solution includes a 4-cent stamp. So in order to make postage of n, you had some 5-cent and some 4-cent stamps, you had at least one 4-cent stamp. If that's the case, you can replace that 4-cent stamp with a 5-cent stamp, and now your total postage has gone up by 1 penny from n to n plus 1. For example, for 15 cents, for let's say 20 cents, you had 5 4-cent stamps. You can just change one of those to a 5, now you got 21 cents. So if P of n's solution includes a 4-cent stamp, replace it with 5 cents. And now your postage is equal to n plus 1. So in that case, P of n plus 1 is true. For possibility 2, P of n's solution only includes 5-cent stamps.
It's got to have at least 3 then.
It's got to have at least 3. And if you have at least three 5-cent stamps, you can take those 3 5-cent stamps, remove them, and replace them with 4 4-cent stamps. So replace with 4 4-cents, and now your postage has gone up by 1, and so again, P of n plus 1 is true. And those are the only possible cases. Either your solution for n involves a 4-cent or it doesn't involve a 4-cent. And in either case, we've shown that we can get n plus 1 out. And so that'll prove that for any n bigger than or equal to 15, we can get the exact postage using only 4 and 5-cent stamps.
Going back to the 5 and 3 cent problem,
Mm-hmm.
if we can prove that it works for 10, 11, and 12, and then we can prove that it works for n plus 3 in 10, then can we do the induction in?
Yes, you could do induction by parts, but I think 11 was what was tripping up my brain.
5, 3, and 3.
Oh yeah, okay, good. Okay, so you could do it for that, yeah, nice. So yeah, his suggestion is you can do induction on different initial cases, right? And show that for each of those initial cases, you can do something like this, a substitution. Cool. All right, so we ran out of time here, but we'll go through this more carefully tomorrow. We'll look at some other examples of induction. We'll look at some more mathematical examples, and then we'll look at a false induction. We'll use induction to prove that all horses are the same color. All right, so we'll get there tomorrow.
There you go.